So let's move on. Our next speaker, Jeff Castle, will talk about flow considerations for scalable, high-productivity protein A membrane. Jeff Castle leads the chromatography products group at W.L. Gore Associates. He has been with Gore for 15 years in both membrane development and product development. Prior to the Gore, he worked at two large pharmaceutical companies in small molecule product development and manufacturing across both drug substance and drug product. Jeff, welcome.
Thank you. Good morning, everyone. Yes, the moderator said, I'm Jeff Castle. I lead the chromatography products group at Gore. Here to talk about another aspect of advanced manufacturing technology this morning following the great talks earlier. This is going to be a much more specific topic on affinity capture, intensification using membranes rather than conventional resins. The overview of the talk today, I'll give a brief introduction of Gore. Then I'll cover some case studies where we've utilized in the recent years computational fluid dynamics to both design our membrane affinity capture products and also characterize their performance. So I'm excited to share this this morning. I also have some data from one of our customers, a CDMO that has adopted the use of our protein A affinity membranes that serves as empirical or experimental confirmation of the modeling data that you'll see that was generated by Gore. So with that, briefly, W.L. Gore and Associates is one of the largest privately held companies in the world. We're almost 70 years now in advanced materials across well over a dozen industries, including bioprocessing. Our company is really built around advanced materials technologies. We are at core a membrane technologies company. We start with high-performance material building blocks, including high-performance polymers, elastomeric materials, inorganics in many cases, and bioabsorbables for our medical device division. And we combine the material building block knowledge that we've generated over the last 7 decades with quite a stable of engineering capabilities. That includes microstructural manipulation, coating and surface modification technologies, composite formulation, and functionalization. So you can imagine we were excited to invest about 10 years back in the world of affinity capture. We have developed over the years, hundreds of thousands of membrane structures that have served all these industries. And so, like I said, about 2017 timeframe, we launched the very first affinity capture membrane for protein A, purification of antibody therapies. We started at the laboratory scale back then, and we've since grown the platform to serve clinical bioprocessing as well as standard commercial scale bioprocessing. Our largest scale membrane devices are 1 liter in size, shown on the right there. And they can be multiplexed or manifolded in parallel to form almost any volume of membrane that you desire. We typically recommend 4 of our 1 liter modules in parallel. That's very suitable for clearing antibody therapies at the 2,000 liter bioreactor scale. We have customers evaluating us at the 5,000 liter scale as well, and we're happy to work with you on facility fit if you're interested in our membranes. So really here, getting into the technical aspects of the talk, we focused on 3 aspects when we developed and scaled our membranes. First, like many other membrane technologies, of course, we focused on speed and capacity, right? So our membrane is a combination technology of both convective and diffusive mass transport properties. So you kind of get the best of both worlds. Like resins, we have, I'm sorry, I need to go back. Like resins, we are able to tune binding capacity based on residence time because the membrane does have some diffusive transport properties. But it also is a high-performance fixed matrix, so you can operate much faster than packed bed resin systems. So our binding capacities range anywhere from 30 mg per mil up to 60 mg per mil, depending on loading residence time, which is much greater than a resin system, obviously, at those same residence times. Secondly, we focused on pressure drop. So it was important to us from a facility fit perspective that our membranes perform as closely as possible to packed bed resin systems with regard to pressure drop, mainly due to limitations of process skids, right? So even at 7.5 seconds residence time, for example, which is where we recommend operating most of our non-loading steps, we see pressure drops around 0.15 megapascal or 1.5 bar, so quite low and reproducible across scales. That's because our membranes are very permeable and they're engineered that way while being rigid. And then lastly, and very importantly, we also focused on elution performance. Again, from a facility fit perspective, we did not want end users of our membranes to have to redesign their downstream process streams to handle large eluate quantities. So we targeted designing our membranes to have elution performance that's very comparable to resin. So these are just some elution curves of a biosimilar trastuzumab that we've tested on our membranes across a number of different size scales. And you can see across all the scales, we're nominally performing at about 2.5 column volumes. That can, of course, be optimized further. It's molecule dependent, as is a lot of things, but we tend to target performance there. So the first example I'll share where we've utilized computational modeling is in the design of our membranes. So when we began designing our membranes, we utilized CFD to design not only the membrane itself, but also the capsules, cartridges that hold our membrane. We worked with customers in our early days of development to then generate actual performance data. We received feedback from our early testers. We refined the design, refined the CFD models, and we ended up with the design that we have today. What we wanted to do not too long ago was actually go back to our modeling team at the corporate level of Gore and actually remodel the commercial device designs that we launched just a few years ago to see what kind of agreement we have between those computational models and our actual empirical performance. So we did just that. Our modeling team utilized one of our 1 ml small lab scale membrane devices and loaded our devices with purified trastuzumab biosimilar across a range of concentrations, and then built a dynamic equilibrium binding and Langmuir model to model binding from a CFD perspective. On the elution side, we decided to use just a first-order kinetic equation to simulate the elution step. So that was what our modeling team did, using the 1 ml binding data as an experimental basis. And then on the empirical side, between internal testing to Gore and customer testing using our 2-liter membrane size, we did some bind-elute experiments with various IgG1 substances. And so what I'll show here is a model visualization of bound antibody release in the elution step. Hopefully this will work there we go. So this is just a computational model of an antibody releasing from our 1 ml size membrane column using those Langmuir and first order kinetic models I showed in the previous slide. And you can see when you apply that model across 3 of our selected membrane sizes, so 9 ml size, which is good for kind of early PD stage, our 58 ml size, which is good for like kind of tox pre-phase 1 scale, and then our 2 liter size, which is suitable for clinical bioprocessing and commercial bioprocessing. The models would indicate good agreement across those 3 sizes. We see about a 2 to 2.1 column volume elution. Note the y-axis here is not in absorbance units because this is mathematical modeling. This is actually simulated concentration of the antibody. By contrast, the empirical results, the 9 ml and the 58 ml column generated, Gore generated data, the 2 liter data generated by one of our customers. Again, across the empirical spectrum there, good agreement across all 3 sizes. And even though there's a bit of an offset between what would be predicted by the CFD model and what is actually observed, we felt like that was pretty good agreement between the modeling tools we had used to design the products and the actual performance. So the next example where we've leveraged computational modeling is we wanted to take our modeling capabilities at Gore and our chromatography expertise one step further to really assess impact to molecule or impact to product. Why did we do that? Well, we were, getting questions from customers, and we were even thinking ourselves, we're operating these membrane adsorbers at much faster flow rates compared to conventional packed bed resin systems. And because of that, are we transitioning into turbulent flow regimes? Do we have to worry about shear forces at such high flow rates? And so, we set out to understand these aspects of impact to molecule or product quality. Before we set off on our modeling journey, we did want to canvass the literature first. And there's an awful lot of literature out there, which was great to see. Along the aspects of shear and shear modeling, we found in the literature that shear alone, absent of any interfaces, actually is fairly unlikely to affect protein quality. Most of us being engineers and not protein scientists, this was an interesting finding for us. But the more we read, the more we realized, shear rates in bioprocessing really range across a broad spectrum. So from 50 inverse seconds up to maybe 20,000 or so inverse seconds. But calculations in the literature would suggest that you really need shear rates of extremely high values, like 10 to the 7th power inverse seconds, to unfold proteins, again, in the absence of interfaces. However, when you add air, water, or solid water interfaces, a lot of those predictions can go out the window. In some cases, the literature would indicate no impact on protein denaturing, and in other cases, there's significant denaturing. And relevant to chromatography operations, there's this synergistic effect of the solid-liquid interfaces within a column, and also duration, right? In our case, a much faster duration, much faster residence time compared to a resin system. On the flow regime side of things, we were surprised to find in the literature that there really wasn't a whole lot of emphasis on the effect of turbulent flow on proteins. And it was stated in a number of the references we found that turbulence, is really not in and of itself a significant issue regarding proteins. But we decided to probe it anyway, just because we wanted to understand. So the objectives of our CFD work, assessing impact to molecule, really were around calculation of hydrodynamic shear rate, cumulative shear stress, and Reynolds number. That might be expected in high productivity affinity membrane chromatography. To do that across size and scale as well. We also wanted to benchmark those calculations by performing similar calculations on a representative packed bed resin system. And then we wanted to go back and run some experimental purifications to challenge our models. And we did that with a customer. So on the method side of things for CFD, we ascertained the flow path structure of our Gore protein A membranes by using an XRCD system, X-ray computed tomography, where we generated three-dimensional models by non-destructively scanning our membrane devices to ascertain the flow volumes. To simulate a packed bed resin system, we used mathematical modeling software GeoDict, and the assumptions behind that were, I think we used an 80 micron bead size, just modeled after several commercially available resins, and just did kind of a random packing model of that bead size. And then simulated the resin bed that way. From a flow simulation perspective, we then took those mathematically generated models of structure on the left. For the membrane chromatography steps, we calculated flow rate through the bed based on a 10-second residence time and a 8 millimeter nominal membrane bed height, or 0.8 centimeter bed height, which is common across our Gore membranes. And then on the packed bed resin side, we calculated flow rates based on a 3-minute residence time through a 20 centimeter conventional bed height. In both modes, we used Siemens SimCenter Star CCM computational software to generate flow velocity fields, as well as calculating shear properties. So the results of the simulations, you can see here, this is just a three-dimensional map of velocity magnitude through the membrane system on the left and the packed bed resin on the right. You can see, just based on the color bars, which are identical left to right, that the velocity vectors through both the membrane and the resin packed bed were pretty similar. And in both structures, Reynolds number was less than 1, so we're at very laminar flow in both of these situations. And that's independent of device bed volume. From a Reynolds number perspective, we also wanted to focus on inlet and outlet tubing, not just chromatographic media, because a drug substance is seeing more than just chromatography media. In that case, you can see the membranes, the Gore membranes, are kind of grouped on the left side of this plot because they're all operated at very short residence times. The packed bed resin is on the right side of the plot because of the longer residence time. But when you look across the spectrum there, the Reynolds numbers are comparable for both structures across bed volumes. And I'll draw your attention to the uppermost curves on the membrane side and the resin side. That would be a 2-liter Gore membrane and a 32-liter resin system. Both are capable of clearing a 2,000-liter bioreactor, and both have similar calculated Reynolds numbers. From a shear rate perspective, we then use the models to calculate shear rate that a molecule would see traveling through these different media. On the membrane side, we did observe higher shear rate, absolute weighted average shear rate on the membrane side, about 900 inverse seconds, as opposed to a packed bed, which is about 300 inverse seconds. So you see about 3 times more shear rate through the membrane, and that didn't surprise us terribly because we're moving so much faster. But what I will draw your attention to are the literature numbers I shared earlier that would indicate that you really need extremely high shear rates to denature proteins up around the 10 to the 7th power, and these figures are much less than that. And then when you run the calculations a step further and you determine cumulative shear stress based on the models, we actually see on the membrane there's a lower cumulative shear stress experienced by a molecule traveling through a membrane compared to a packed bed resin system. And we suspect that's because of the bed length difference, right? So on the membrane side, you're about at 1 centimeter. On the packed bed side, you're at about 20 centimeters. So that seemed to check out for us. We also took that a step further as far as flow components. So we didn't want to look only at chromatographic media, but also flow components. Within our membranes, we have fluid distributors, and we have an air trap built in. So we wanted to factor in those components. And we saw across the scale of those flow distribution components very low shear stresses. And when you look, again, these numbers are all quite small compared to the literature values that would be in a concerning region. So in summary, on the CFD modeling side of this talk, we saw extremely low Reynolds numbers across both membrane and resin media. Weighted shear rate average was higher for the membrane as we expected, but cumulative shear stress that's experienced by a drug substance is actually lower for the membrane. And both shear rate and cumulative shear stress are relatively low for both of these systems compared to literature research that has probed interfaces in the past. Of course, we wanted to challenge this empirically. So, really want to thank one of our customers and early adopters of Gore membrane technology, AGC Biologics. This is all AGC Bio data and shared with their permission. They performed a commercial scale assessment of Gore membranes recently. They utilized 2 1-liter Gore Protein A devices arranged in parallel manifold, as you can see in the upper right picture. In this case, they grew up a batch in a 2,000-liter bioreactor suite, and they set out to purify 500 liters, a small aliquot from that batch, to see how quickly they could purify 500 liters using Gore membranes. The chromatographic overlays are shown here for the 19 cycles that it took to clear 500 liters of that harvest. They saw very high reproducibility from cycle to cycle. This is all 19 cycles overlaid. They also observed our characteristic narrow and sharp elution, roughly 2.5 column volumes across every cycle. From a pressure performance, processing the 500-liter aliquot, they saw very consistent pressure from cycle to cycle, and well below the system maximum operating pressure of 4 bar. I believe they used an Actor Ready XL system with a high flow kit for this. They also changed their protocol midway through. I think after cycle 10, they reduced the CIP step by about half to see if they could first, reduce cycle time, but second, whether or not there would be any impact on pressure rise due to cleaning less aggressively, and they didn't see any. So their results, adding in here some laboratory scale results on the left. In the lab, they ran a 5 ml pre-packed Pro A resin column. I think it was a MabSelect Shore, if I'm not mistaken. They ran that against a 3.5 ml Gore membrane device, and they saw a 10-fold increase in productivity with otherwise no impact to chromatographic process performance and product quality and process impurities. They also measured SEC product quality distributions. They found that the main monomer was comparable between membrane in green and resin in blue. Aggregates were comparable between membrane in green, resin in blue, and low molecular weight species were typically less than 0.04 area percent, so they weren't plotted. AGC also elected to do some additional product quality analysis between the membrane and the resin at lab scale. So from a charge variant distribution perspective, you can see that the resulting product was basically identical between the Gore membrane and the resin system. And then on the right, they also ran N-glycan distributions, and they were also very similar between membrane and resin. And so AGC utilized this data, really internally to convince themselves that regardless of the media used, that they had confidence that the resulting product quality and process impurities would be similar, whether using a conventional resin system or a membrane system, giving them confidence to promote the use of membranes to their customers. And again, these results really do align well with the modeling data that I shared earlier, that even though you're operating a membrane 6 to 20 times faster than a resin, you can expect comparable product quality performance. So in conclusion, hope this has been helpful for everyone to hear. We believe that the Gore Protein A membrane devices can provide dramatically increased productivity through your Protein A affinity capture step with high binding capacity, short residence time, low pressure performance, and also very, very sharp elution performance. We also believe that we're a low risk to adopt, right? So you can expect comparable product quality to resin with much higher productivity through both the CFD modeling evidence and the empirical evidence. We're happy to provide you with a lot of regulatory support information if you're interested in trying our membranes. We have validation guides, an extractables packet. We have viral clearance information, and plenty of stewardship information that can help on the regulatory side as well. So with that, thank you. I want to really acknowledge Eric and Hassan on our technical team and our modeling team at Gore. Special thanks to AGC Bio, their sites in both Bothell, Washington and Longmont, Colorado, for running various membrane trials over the last several years. And with that, I'll take any questions.
Great talk, and very exciting to see the Protein A membranes coming to the world. A few questions. Number one, do you have viral clearance data?
Yes, great question. We do. We can share that if you have interest. We don't have that posted on our website, but through an inquiry, we can send that to you. In summary, we demonstrated roughly between 2.5 and 3 log viral clearance through our membranes.
Okay. The second question is the life cycle analysis, compare the resins and the membranes. Have you done that?
Yes, so not shown here, but we have a white paper that we actually wrote with AGC Bio that basically documented a comparability study on life cycle that we can share.
Thank you.
Mm-hmm.
Any other questions?
Great talk. Just wondering, with 19 cycles at 1 liter scale or 2 liter scale, what's the buffer usage? Have you done any cost analysis on that?
Yes, we have. Great question. I don't have that off the top of my head in this particular study, but in general, we do see in increased buffer usage with membrane, just because of the number of cycles compared to a conventional resin system. In general, using the cost of ownership calculation tools that we've developed at Gore, you can expect to see anywhere between a 10% and maybe 35% increase in buffer use with membrane. I think that's fairly common, not only to Gore membrane, but a lot of membrane systems. That said, we do believe the increase in productivity that you gain, and certainly the cost difference, because you're using so much less protein A with a membrane compared to a packed bed resin system, the cost savings of the membrane far outweighs the extra cost of a little bit more buffer. Sure.
Thanks for sharing the great content on CFD analysis. Were your team able to do any CFD analysis of air-liquid interface or solid-liquid interface?
Great question. No, we did not go that far yet. We would love to. But the extent of CFD analysis we've done is what I've shown here. But if you have suggestions for us, I'd love to talk afterward.
Sure, definitely. Thank you.
Great. Thank you.
Do you have any other questions? All right. Thank you for all the questions. Jeff, thank you for excellent talk.
Thank you.